All right, so this is the final part of our stoichiometry with precipitation reactions. This is a lot shorter amount of steps. We're going to basically be given the amount of precipitate that forms, and then we'll work backwards to figure out like the original molarity or the original volume of one of the reactants that was used. So for this first one, it says we have an excess of cobalt 2 chloride. So this is my reagent excess that's combined with 35 milliliters of a potassium carbonate solution. And remember, this would then be my limiting reactant here. Assuming that the reaction goes to completion, 8.11 grams of a dry precipitate forms. Determine the original molarity of the solution. So what I want you, and specifically the potassium carbonate solution. So first off, you need to be able to, again, write these precipitation reactions. You need to be able to balance it and also identify what our precipitate is, because it doesn't tell you which is the dried precipitate. You have to be able to identify that yourself. So then once we have our balanced equation, we're going to jump right in with the stoichiometry, starting with our grams of that precipitate. So that says I have 8.11 grams of my cobalt 2 carbonate precipitate. I'm going to put that into moles. So I'm going to use its molar mass, which is 118.94 grams, which would give me 1 mole of my cobalt 2 carbonate. Okay, now I want to know how many moles of my limiting reactant that would have been formed from. So I'm going to use my mole to mole relationship here, that for every 1 mole of my cobalt 2 carbonate that was produced, it must have been produced from 1 mole of my potassium carbonate. Okay, once you plug that in, you're going to get how many moles of potassium carbonate were present. Sorry, on my K2CO3. Okay, so that is the amount of moles of that potassium carbonate. That was my limiting, so I know that this was the total amount of moles that were present. From there, I have my moles and I have my volume, so I can quickly figure out the molarity. So the molarity of that potassium carbonate would be equal to that 0.0682 moles that we figured out were present, divided by the 0.0350 liters, which then goes ahead to calculate 1.95 molar. So again, that's my concentration of my K2CO3. Okay, so number 6 is just like it. 7 is very similar. If you jump down a little bit, you're given very similar information, except in this case, you're given molarity of the limiting, and then you're given the amount of precipitate, and you're asked to find volume. So you can kind of assume here what that part, is going to look like. Let's go ahead, write the balance equation, make sure it ends up being balanced out. And in this case, keep in mind when you're looking at which one's going to be your precipitate, while you do have SO4 here, it's with the potassium ion, which is always soluble. So that has to be my aqueous product. So it's our copper 2 chromate solution that's going to be our precipitate here. So when you go ahead and figure out this one, I would have 12.3 grams of my CuCrO4. I'm going to add up its molar mass and get 179.55 grams. Gives me 1 mole of my CuCrO4. And then in that mole to mole relationship, for every 1 mole of CuCrO4, it's going to be produced by, 1 mole of my CuSO4 solution. Because remember, this was the one that was our limiting here. Now I can go ahead to figure out and use my molarity here if I want, because I know based on the molarity that for every 0.64 moles of my CuSO4, I'm going to need 1 liter of it. So when you go ahead and actually plug that in, so 12.3 divided by the molar mass divided by the 0.64, you should get here, and I'm going to go to the 3 sig figs that I had for my grams here. I get 0.107 liters, and that would be my answer. All right, so that's one other way to do it in terms of getting the volume, and 8 is going to be very similar to that. Okay, so that's it. All you have to be able to do, and again, that's the last part of this stoichiometry with our precipitation reactions.